Hello, today I'd like to talk a little bit about helical gears and how they can be used in some transmissions to set some desired gear ratios. So we're going to have some fun. It assumes you know a little bit about tooth numbers, dimetral pitch, pitch diameter, pressure angle for spur gears, and this assumes you know a little bit about gear ratio and what you have in machines. We're going to start today with a helical gear discussion, and then we're going to dive into some gear trains. We're going to look at some compound gear trains, and then we're going to see a cool application. And that's going to be a Ford Toploader transmission. First, reviewing a gear ratio, you always want to be careful what this ratio is a ratio of. This would be for a rotating gear pair. It'd be the speed of the input. Lowercase n is speed, so that's the speed of the input divided by the speed of the output. That's how your gear ratio is defined. Dimetral pitch, on the other hand, is the number of teeth divided by the pitch diameter. And this is for rotating spur gears. We're going to start talking about helical gears, and I want you to be comfortable with the term transverse dimetral pitch. And it's really the same thing. You have a number of teeth divided by diameter, but there's a specific dimetral pitch called transverse dimetral pitch. So for parallel axis helical gearing, the teeth are canted at an angle. The angle is psi, that's the helix angle. You have a normal pressure. Your pressure angle that you had before is now referred to as a normal pressure angle. You have N, capital N, is the actual number of teeth on the gear. The pitch diameter now would be what you would see in a transverse plane. So a transverse plane is a plane that is cut perpendicular to the axis of rotation. As you can see here, you see the circle of the pitch cylinder of the gear, and that is the diameter. So that leads us to the notion of transverse dimetral pitch, and that would be the actual tooth count divided by that D that we just spoke of. There's some other gory details and some other parameters, and I'd like to introduce those briefly. The phi sub n is the normal pressure angle, but phi sub t is the transverse pressure angle. And then there's, to complement the transverse dimetral pitch, you have the normal dimetral pitch. And these values that we've been speaking of are related to the cosine of psi, cosine of the helix angle, in the following way. The cosine of psi is transverse dimetral pitch divided by normal dimetral pitch, and it is the tangent of the normal pressure angle divided by the tangent of the transverse pressure angle. We're getting into the weeds here a little bit, but there are different ways of looking at the diameter in a normal. If you were to take a normal plane view, where you would think in that view the teeth would actually be straight, would look straight. There would be an ellipse that you would be cutting relative to the original pitch cylinder, and that ellipse will share a curvature, the same curvature as what I'm calling the normal diameter, and that shared curvature would be at the minor diameter of the ellipse is where they share that. In the book, they talk about a virtual number of teeth, and I actually investigated this and challenge you to as well. But if you were to take the normal dimetral pitch times that normal diameter, you'd actually get something that looks pretty quirky, and it makes it look like you've gotten more teeth. And the book talks about why that's a positive for helical gears, that appearance of more teeth. So anyway, so helical gearing, that kind of gets us started there. What to look for. Here's an example. I went on to Boston Gear. You've also seen me look at Rush Gear. Boston Gear is another good example. And here we've got the 6 transverse diametral pitch of 6. They're showing 14.5 normal pressure angle, 45-degree helix angle. So these are gears that you can actually get. So 6 transverse diametral pitch. And if you zoom down to my favorite example of 18 teeth, you see that the pitch diameter is 3. So I wanted to show you that. So now let's go take a look at the train value, which is a value that is discussed in the Shigley book. Here it is in the numerator. You have the product of the gear teeth of these. Let's say there's P driving gears. So those are the input gears. So you take the product of your input gear tooth numbers and put those at the top, the product of all those, and you divide by the product of the K driven gears, and those are the output gears. So you put input gears on the top, the product of those, and then you may have K output gears. You put the product of those on the bottom. And you're going to multiply it. The thing with the train value is it likes to take care of the signs, the SIGNs of the rotation and the directions of rotation. So the way that's done is you use a -1 to the M power, and M would be the number of external gear meshes that you would have. Let's do a trivial example. Here I've got an input gear 2 feeding an idler gear 3, feeding an output gear 4. So gear 2 is a driving gear. Gear 4 is a driven gear. The quirky thing here is that N3, gear 3, is both a driving and a driven gear because it drives 4, but it is driven by 2. There are 2 external meshes here, the one between 2 and 3 and the one between 3 and 4. So M is 2. So the train value now would be equal to a -1 to the squared, which is of course 1. And then you have the input gear tooth numbers on the top, so N2 and N3, and then you repeat N3 because it's also an output, and then 4 is your output. And then of course you simplify it and you get the N2 divided by N4, so those are your gear tooth numbers. We want to take that and go back and look at our gear ratio stuff and see what that looks like and compare it. Remember that your lowercase n denotes your speed or your RPM. We define gear ratio, say between the gears 2 and 3, to be N2 divided by N3, or the speed of the input divided by the speed of the idler. And that's actually equal to, if we take care of signs, we're looking at them rotating in opposite directions. So that's actually equal to the number of teeth on gear 3 divided by the number of teeth on gear 2. Similarly, 3 and 4, the gear ratio for 3 and 4, that stage would be the speed of, defined as the speed of 3 divided by the speed of 4. And we know that's equal to minus the number of teeth on 4 divided by the number of teeth on 3. If you were to put it all together, sort of a compound machine, 2 is your input, 4 is your output. So it would be defined as the speed of the input 2 divided by the speed of the output 4. And we know that that's actually equal to the product of the 2 stages, where I take this part here, plug it in there, and this part here and plug it in there, simplify it, and we get N4, number of teeth of the output gear, divided by N2, the number of teeth on the input gear. Again, where N3 cancels and the 2 minus signs combine. If we want to compare our train value, you recall that the train value is capital into number of teeth on 2 divided by number of teeth on 4. And then we want to compare that with the gear ratio of 2 to 4. And we found that was the number of teeth on 4 divided by the number of teeth on 2. we see that the train value and the gear ratio are reciprocals, something I've said for a while. And the train value, if it's a reduction, the train value is actually less than 1. Let's go take a look at this book example. So here we're going to treat gear 2 as the input, and we're going to treat gear 6 as the output. So the way the book wrote it as the speed of the last gear, capital L's last, is equal to the train value times the speed of the first gear. So first gear is N2, so that comes up here. And the last gear is N6, so that is here. So this value here is the purported train value. So let's see how this kind of flows. The second gear feeds the third gear, which is an idler. That third gear feeds the fourth gear. And the fourth gear is on the same shaft as the fifth gear. So 4 and 5 rotate at the same speed, and then 5 drives 6. Okay? So if we were to take as our inputs, N2 is an input, as you see there. N3 is an input because it's driving 4, so we put it there. N5 is an input because it's driving 6, so we put it there. Then looking at the outputs on the bottom, we've got 3 on the bottom as an output because it's driven by 2. 4 is driven by 3, so it's there. 6 is driven by 5, so it's there. And that takes care of all of the gears and their relationships. There are 1, 2, 3 external meshes, so you have -1 to the third or minus. So that is your train value. It's kind of interesting to look at this and figure out, hey, is this a reduction or is this an increaser or an overdrive? And let's think about that. You know, this first stage of 2 going to 4, that is a reduction as drawn because the pinion N2 is smaller than 4. So that's a reduction. The crazy thing here is that 5 is bigger than 6. So that's an increaser. So you would not really want to do this in practice. You'd have a reduction and then you go and have an increase. That's a little bit crazy. But anyway, that's looking like what this is describing. So I want to rework 3 of the book's problems. And those example, the Shigley book has the examples 13.4, 5, and 6. Those are actually overdrives or increasers. So I'm going to kind of tweak those and let them look like they're reductions. What follows now. So here, compound gear train. Now this is as a reduction. And in class I talk about, you know, it's kind of tough to get that more than 10 to 1. Typically you're more like 3 to 7 to 1. You don't really get to that 10 to 1 kind of thing because if you did, your output gear would be 10 times bigger than your input, and it kind of gets tough to fit it all in there. Anyway, so let's take a look at an example where so this is an in view and then a side view where I have an input pinion N2 feeding its output gear N3, and then on the same shaft as N3 I've got N4. So N3 and N4, gears 3 and 4 rotate at the same speed, and then 4 drives 5 for the output. So it's called a compound gear train. It's a compound machine, and it looks like a reduction because I've got N2 smaller than N3, and then at the same speed N4 is smaller than N5. So what we're going to do is we're going to look at trying to achieve a gear ratio of 30 using these 2 stages right here, with 2 as the input and 5 as the overall output. Okay, so that's what we're going to try to do. So we can say that G25 is 1 over the train value, or -1 squared, since there's 2 external meshes. and then our outputs would be N3 and N5, and our inputs would be N2 and N4. Okay, so at a minimum, the Shigley book talks about the minimum for number of gear teeth on a pinion might be about 16, depends on the pressure angle. But let's say that we're going to do an N2 and N4 of 16. So 16 here and 16 there, and kind of see what we can do with that. So if we want 30 for G25, and we're going to propose 16 for both of these, then we would have the product of N3 times N5 looking like it wants to satisfy that equation. So let's see what we can do with that. So if we were to say, hey, what if N3 equals N5, you would get something that looks like this, and you could actually solve it. You'd get 16 times the square root of 30, which is 87 and some change. You could round it up to 88. And then that 88, if you were to use it back and figure out what your actual G25 is, since you can't have a fraction of a tooth, obviously, so you round it up to 88, and if you go check your gear ratio, you would actually have two stages of 5.5, and that would be a 30.25 gear ratio, pretty close to 30, and that would give you N2 and N4 both being 16, and then 3, and then 5 being 88. So that's pretty close. What if you were to say, on the other hand, that we're going to split that 30 up into a stage of 5 and a stage of 6? So that's what we're trying to do here. And if you were to do that, your pinions would again have the 16 teeth. But one of the outputs, say N3, would have 80, and the other N5 would have 96. And when you did that, you would get that exactly 30, which should be pretty cool, just separating it a little bit. So you can play around with the tooth numbers to get your desired situation. So now I want to take a look at a compound reverted gear train, and this is one where the input and output, you just take that compound gear train and you set it up so that the input and the output are collinear. And it's really nice. It helps reduce the size of your system when you can do that. I like it. And what that means is that N2 feeding N3, N4 feeding N5 again. So 3 and 4 on the same counter shaft. And what that means is that the center distance between your input gear and the counter shaft, that's going to be D2 over 2, the radius, plus D3 over 2, the radius of the third gear. That center distance has to equal the center distance for the other gear pair, and that's going to be D4 over 2 plus D5 over 2. And if you say that we're going to use the same transverse, if they're helical, dimetral pitch throughout, then that kind of helps you, because you can substitute for the D, you could substitute N divided by the dimetral pitch. So you take this equation and you substitute the tooth numbers for each gear divided by the dimetral pitch. You get this equation, and you can multiply through by the dimetral pitch, and you get an amazing equation here where you have the sum of tooth numbers being equal for each stage. So sum of N2 plus N3, that stage, if it equals the sum of N4 and N5 for the output stage, and again, all same dimetral pitch, then you're going to have your center lines lining up, same center distance. Let's take an example. Let's say we want that 30 reduction again, and we're going to sort of separate it so that N3 equals 6 times N2. So N2 is our pinion, N4 is a pinion. We're going to let the outputs be 6 and 5 respectively, times those. We're probably going to have different pinion counts, but we're going to stick with the sum of tooth counts being equal for the two stages. So I'm going to start by proposing that N2 is 16. So if I stick 16 in for N2, and N3 is 6 times 16, that's going to be 112. So the sum of gear teeth would be 112, and that would be N4 plus N5, which is 5 times N4. So if I were to solve for N4 from that equation right there, I'm going to get 112 divided by 6, and that's going to be 18.7. And so that's, oh no, we've got we've got a fractional tooth count, so that's not going to work. So then let's try 17. So 17, what that means is you're putting 17 in for N2. You're going to repeat this, repeat and rinse. So that's 119 once you take N2 plus N3, and then you're going to divide by 6 again because you're going to try to solve for N4, and we're still at that fractional. But guess what? Once we try 18, we've hit a home run here because we've got 18 is N2. When you take 18 plus 6 times 18, you get 126. Divide by 6, you get to 21. So that's going to actually work. In order to do that, here's what I did. I took and just created a spreadsheet and said, okay, I'm going to have my N3 is going to be 6 times 16. I sum those two up, and then I take the sum of those and divide by 6, and I just repeated, basically took this line, copied, pasted it, increment, and found that 21. So that's how I did that. Okay. So, yeah, in summary, I've got the N2 pinion coming in at 18. I've got my N3 coming in at 106. That's a 6-to-1, that stage. I've got my N4 coming in at 21. And then I've got my N5 at 105 for a second stage of 5. The overall gear ratio is 108 times 105 divided by 18 times 21. That's 30. And if I take, as an example, which I'm going to use in a moment, with my transmission, I want to say, what if my transverse diametral pitch was 5 teeth per inch? I could take the center distance as the sum of the two teeth, 2 and 3, divided by 2 times the pressure transverse diametral pitch. That's the same as N4 plus N5 divided by 2 PT. So that would be 126 divided by what looks like 10 teeth per inch, or it's 12.6 inches center distance. So these are big gears, I guess, aren't they? Wow, we should be able to carry some power. Got some face widths on those. Okay, speaking of power, let's look at my Ford Toploader. Get this off of David Key Toploader Transmissions Inc. Let's go take a quick peek at that. So that's what it looks like, and he's got a lot of information here. The cutaway view is the one I like to show, and then the torque specs and gear ratios, I like to show that one. The one I have in my office is a wide wide ratio. Yeah. So anyway, I like this thing here, and the way it works is, and these are the ratios. The way it works is you've got power coming in on this input shaft. The engine's over here. Power comes in on the input shaft. This is the first gear, which has actually a tooth count of 23. It feeds these gears down here. This is called the counter shaft, and that particular gear has a gear count of 30. So he's labeled it as counter gear tooth counts. So say we're in first gear. So if we're in first gear, then the 23 feeds the 30, and then over here's first gear, and that's going to be a 15. So that 15 feeds a 32, and then that's connected to the output shaft that goes out the back end of the vehicle. He's got that listed as a 2.78 gear ratio. Yeah, so let's go around and let's play with that. See how that 278 comes about. So 23, 30. 15 and 32. Yeah, so this is my little mock-up of it. So I've got the input shaft feeding this NI, so that NI I'm going to say is 23. 23 feeds the 30, that's the NC, the counter gear. Coming over here, I've got 15. That's my first gear on the counter gear, and that's feeding the output. What was that? That was 32. So 23, 30, 15, 32. So that's what that one would be. So take a look at this from an Excel perspective and see what we get. This kind of set up too. So so that was the 18 feeding the 108 to give me a 6 as that first stage. And then I've got 21 feeding the 105, giving me 5 for that second stage, and the overall was 30. So I've actually put a $sign on that, multiplying these two together, and because I'm going to go and add some rows later. And then I did my diametral pitch over here, transverse diametral pitch, because I wanted to see, well, what do these diameters look like? And so that's how you get your diameter. Two numbers divided by the transverse diametral pitch, and then center distance is the would be the sum of the diameters divided by 2, obviously, and then you could check the tooth counts. That's the kind of thing I was doing there. Okay, so let's say that that's NI, that's NC, that's N1C, and that's N10. And I've got 23 feeding a 30, feeding a 15, feeding a 32. So yeah, let's go back and look at this guy. Okay. Okay, you can see it now. Yeah, so the 23 feeding a 30, so that's my first stage. And then the output, the counter gear 1C, is going to feed the 32. And according to the site, it's a 2.78 overall gear ratio. And here are my pitch diameters. And wow, looks like my end check is not checking out. Interesting. I wonder if they have different diametral pitches. The gear teeth, the gear ratio is agreeing. Let's do the others now. So I could take these two columns, or rows, beg your pardon, take them and copy them down, and then repeat for second gear, because it has the same first stage. So second gear is 21 feeding a 31. 21 feeding a 31. And overall is 1.93. Agrees. So I'm feeling pretty confident about this. Let me go and copy that again. So that's N3C, N30. And I've got a 24 feeding a 25. Almost a 1-to-1. And that's showing up as a 1.36 overall, which is what he has. And of course, fourth is direct drive. So it's 1. That's just connecting the input directly to the output. So isn't that interesting? It seems as though the center distances, well, they must have different diametral pitches on these, because the tooth numbers don't seem to be adding up. I've got B4 plus B5. B4, B5 is there. And that one is B3 and B2. Yeah, it doesn't look like it. Interesting. So, in order to get the different diametral pitches, or different, I'm sorry, center, in order to get the same center distance, they must have used different diametral pitches there. Slightly different. Anyway, so in summary, we've reaffirmed some tooth numbers: diametral pitch, pitch diameter, pressure angle for spur gears. We've discussed gear ratio. We've looked at some helical gears, parallel axis. We've investigated some gear trains. We've studied some compound gear trains, reverted one where the input and output shafts are collinear. And we saw a cool application with the Ford Toploader. I hope you've enjoyed it.